Good morning, Stockholm. How are you?
Morning, we're fine.
I'm happy to hear that. Are you ready to hand in your homework?
We did.
Okay. Then we'll move right along. I'll look at the homework and see if there's further discussion required. In the meantime, we have moved on to Flutter, and you're reading chapter 3, I'm sure. Probably have already finished reading chapter 2, but at least as you've begun reading chapter 3. And you have now mastered, is it right out there? You've already mastered Lagrange's equations from your previous coursework. You are now somewhat familiar with Hamilton's principle. We'll become more familiar as the course goes along. And we want to discuss at the beginning of chapter 3 and the material therein, flutter and the physical phenomenon of flutter. There's a counterpart to divergence, which is a static phenomenon, which is the dynamic instability known as flutter. There's really no dynamic counterpart reversal. Reversal is a static concept. I mean, you could do a dynamic analysis of reversal, but you wouldn't gain much. On the other hand, there's another phenomenon that we'll treat later on called gust response, and that's the dynamic response to atmospheric turbulence, otherwise known as gust. So just as there are two great physical phenomena in static elasticity, namely divergence and reversal, there are also two prominent phenomena in dynamic elasticity, namely flutter and gust response. The counterpart in turbulent machinery, for those of you who like turbulent machinery, I think they call it inlet distortion. Because in both cases you're talking about some random pressure fluctuations in the flow that lead to the dynamic response of the structure as the structure interacts with that flow. In the case of turbulent machinery, it's the incoming inlet distortion. In the case of an overall aircraft running with atmospheric turbulence, is moving the entire airplane. Well, let's first of all talk about flutter, and let me remind you of what we've done the other day. There are basically going to be two kinds of flutter we'll talk about. There are probably at least a half a dozen types of flutter that someone thinks about. But from a fundamental point of view, there are really two that people often think of. One is single degree of freedom flutter. That means I only need one mode or 1 degree of freedom. Due to negative aerodynamic damping. That doesn't mean you necessarily can only look at one mode, but what it does mean is you can look at each mode one at a time, individually. If I have 13 modes that might experience this kind of flutter, I can look at each mode separately. Or in the case of turbulent machinery, if I have a cascade, all of the blades may be moving more or less the same way, except there's a phase angle in time between the blades, right? So now you have to find the phase angle that is most likely to lead to the most critical flutter condition. Right? In turbulent machinery, you have that. In the case of airframes, typically you might have a few dozen modes in a flutter analysis done by an aircraft company, and you have to look at all of them to see which one might exert flutter. It turns out that this kind of flutter is really prominent in turbulent machinery. In fact, for a long time, turbulent machinery people didn't really think about anything other than single degree flutter, but there are other kinds of flutter to think about. So this is prominent in turbulent machinery. It's also most likely to occur on control surfaces if you're talking about airplanes. Most likely to occur on control surfaces. You don't know that. I know that. People have been working in the field for a long time know that. And we'll talk more about later why that is so. And it's also most likely to occur in transonic flow. Actually, almost any kind of flooding is most likely to occur in transonic flow. So in a high-performance airplane, you find the dynamic pressure of which flutter occurs, and you can plot that versus Mach number. And usually it's in the range of Mach near 1 that you are most likely to encounter flutter. That's also where the theory is weakest and most questionable. Okay. That's why people are still doing research on this topic. Okay. So it's most likely to occur in transonic flow if you reach that condition. So this is true not only for spin breathing flow, but also for other kinds of flow in transonic flow. So if single degree of freedom flutter is one kind of flutter, the only other possibility is multi-degree freedom flutter. But often you only need 2 degrees of freedom to describe qualitatively what's going on. You may need a dozen degrees of freedom in your analysis to get a good quantitative estimate of the flutter condition. But usually 2 degrees of freedom, or in some cases 1 degree of freedom, is sufficient to give you a qualitative indication. So if I'm doing an analysis before they really define the airplane, it's a paper airplane, right? You're thinking about a new airplane. You have a vague notion what it's going to look like, and maybe how many engines are going to be on it. You have a rough idea of what Mach number you want to fly and so forth. I'll probably do a lot of 1 and 2 degree freedom flutter analysis, except it's in a ballpark answer. So multi-degree freedom flutter. Often 2 is enough, at least qualitatively. And again, as before, it's most likely to occur in transonic flow. It doesn't happen too often in turbine machinery, but it can. And it can happen with control surfaces, but it can also happen with the overall wing or tail, vertical or horizontal. Okay? So that's sort of the big picture. So let's now talk a little bit about each of these. And we can talk about them in different ways. We can start out with our typical section model of the spring, right? Yeah.
Question about multi-degree of freedom flutter. Maybe we're going to get into this later, but you said it can be like, you have to take as much as like over 10 degrees of freedom to qualitatively describe it.
Yeah. Quantitatively describe it.
Quantitatively.
Not qualitatively. Usually there are 2 principal modes of double mode flutter.
Mm-hmm.
The challenge is you may not know ahead of time which 2.
Okay.
Right? Is it 2 associated with the wing? Is it 2 associated with the horizontal tail? Is it 2 associated with the vertical tail? There's a combination of rigid body pitch and the bending mode of a wing. There are usually 2 critical modes. Usually, a couple of them flutter. But you don't know what they are until you saw them. Okay. Now, if you've been doing it for 30 years, you may have a guess. You're building an airplane that looks a lot like the last airplane. So you think, well, last time it was first bending the first portion of the wing, probably still is, right? So you pay special attention to that. But sometimes you get surprised, right? A mode that you didn't think would be critical turns out to be critical. And there are numerous cases of that happening in real airplanes. And that's one of the challenges, because in a real airplane, you may have to, once you get to hear the final design, you're talking about dozens of modes that may have the potential for flutter. And you want to be careful not to exclude some possibilities that might be the critical one. Okay, so again, as in stack aeroelasticity, we can look at this spring model. We can look at a simple wing model like this, which has a well-defined elastic axis. Or we can look at something that doesn't have an elastic axis, it might be a typical case would be a delta wing. Now this has plate-like deformations, meaning it bends along the chord and it bends along the span. This has what is usually called beam rod deformations. That is, the elastic axis bends like a beam, but then there's a twist about the elastic axis, so there's a rod-like torsion, and you need to account for both of those. And of course, in this case, for coupled mode flutter, this model can exhibit coupled mode flutter, but to do that, we have to have two modes. So we need not only torsion in this model, but we also need translation, or this is the counterpart of bending of the elastic axis, right? This thing translates up and down on this vertical spring, but it also twists about the elastic axis. So when you're doing a roll airplane, you're probably using this model, or you might be using this model. You're probably not using this model, except you might use that model in the very early stages of the new design. You might. It turns out that, not surprisingly, that this model you can think of as a special case of this model. Well, how's that? Well, this model has an infinite number of modes in both bending and torsion. But if I only keep one bending mode and one torsion mode, I have 2 degrees of freedom, and then the mathematics looks just like the mathematics is. The coefficients have a different physical interpretation, but mathematically these are the same if I only take 2 modes in this case. This case, if there were elastic axis, I could start out with a plate-like model, but it would reduce to this model if there were elastic axis. But usually, since someone's designing a wing or airplane, they know whether they're going to build it so that it has beam rod-like structural characteristics or it has plate-like structural characteristics. This is typical of low-speed aircraft. This is high-speed. Okay, so we need to look at all of these. So let's look at this one first, and much of this is discussed in the book, so I'm going to sort of skim through it and give you the highlights, because all of the basics of the flutter mechanism is the same, whichever model I use. Right? The mathematics gets a little more elaborate as I go from this model to this model to this model. You know, given your great facilities mathematics, that's a mere detail, right? So there were some smiles here. That was meant to be a humorous comment, Stockholm, if you can. Sometimes humor doesn't translate well when you go across the Atlantic. Either way. I have a couple of stories about that, but I can't tell them. So. Anyway, okay, so let's look at this one first. We'll call this the typical section model. By the way, it's called the typical section because people think of this representing a choice of a section of this wing, right, and treating that section. We pretend like there's some span-wise location that's typical of this wing, and this represents the dynamic of that section. Actually, that's not a really good way to think about it, but that is historically the thought process. If you really want to think about the fact that this only has 2 modes of mathematics, is pretty much the same. Okay, so let's look at the typical section model first. And let's do both 2-degree freedom flutter and, in this case, just 2-degree freedom flutter. And this is really recapitulating what we said the other day, and I think repetition has its charm as well as its value. So let's be a little bit repetitive. I need to write down kinetic energy, which is 1/2. And I won't go through the details of this, but you may remember it's 1/2 m times h dot squared plus s alpha times h dot ch, I think. H dot alpha dot plus I alpha dot squared, where we're assuming that we have a translation of this spring point down and a rotation about that spring point positive no touch, right? And this is the total mass of this wing. This is the moment of inertia about this point. And S alpha is the total mass times the distance from the center of gravity, wherever it happens to be, to the elastic axis. Right? That's what it turns out to be. And the kinetic energy, the potential energy, is 1/2 K alpha alpha squared plus KH H squared. And one reason we choose H and alpha to be associated with the elastic axis is because it simplifies our writing of the potential energy. We could also use H and alpha as being the translation of the center of mass and the rotation about the center of mass, right? In which case that would simplify the potential, the kinetic energy, because this term would disappear, but then there would be a cross term down here. I mean, there are two different alternative coordinate systems, right? They would presumably give you the same physics. They would give you the same answer for water, right? This is the traditional choice. But there's nothing magic about it yet. Where it comes from? Oh, this term? Oh, actually, it's 2 times what I call S alpha. Is that what you wanted to know? Yeah. And S alpha is equal to the mass times what I call x of CG, where this is the distance from CG, center of gravity, to the elastic axis. And then the virtual work is equal to the moment about the elastic axis times delta alpha. Oops. I'm getting ahead of myself. I'll have an interval when I get to the next model, but not here, right? M sub y times delta alpha, right? That's the work done. That's the virtual work done by the moment about the elastic axis. And this is the work done by the lift force acting through the reflection of elastic axis. And there's a minus sign because L is positive up and H is positive down. And I didn't do this, folks. I mean, this was done 50 years ago, but it's traditional in this work. And so, if you're going to read the rest of the literature, you might as well love the minus sign. Okay? All right. Then, if we use all of that and we put it into Lagrange's equations, where H and alpha are the generalized coordinates in a Lagrange equation formulation. So we have a Lagrange equation that looks like d dt of the partial of L, with respect to H dot, minus partial L with respect to H equals Q sub H. Okay? And L, of course, is defined to be the difference between the kinetic and potential energy. And Q sub, and the virtual work, the definition of these Q's, and there's also a Q sub alpha, is Q sub H times del H plus Q sub alpha times del alpha. This is the definition, not of virtual work, it's the definition of Q sub H and Q sub alpha. It's the thing you multiply del H and del alpha by to get virtual work. So the way this works is unintended. Is that too sudden? No, I saw a smile or something. The way this works in virtual work is you have to be able to physically reason what the expression for the virtual work is, and then identify the coefficients of the virtual changes in generalized coordinates to give you the generalized forces, namely these things. So this is the equation for H, and then there's a similar one for alpha, which I won't bother to write now since it's the same thing, except H is replaced by alpha. Right? And if you do that, a few lines later, you get the equations of motion, which are mh double dot plus k sub h times h plus s alpha times alpha double dot equals minus L, that minus sign, right? And then you have I alpha alpha double dot plus K alpha alpha plus S sub alpha is the same as, I don't know why they don't call S sub alpha H, but they don't, right? In the literature, it's always S sub alpha. Seems like they're not giving proper recognition to H, but what I'm saying. H double dot equals M sub Y. Okay? And now the remaining thing I have to do is I have to write down some expression for L and M sub Y. And as we'll discover as we go on the course, there are many levels, just as there are many levels of structural modeling, there are many levels of aerodynamic modeling. So there's probably 3 or 4 different levels of aerodynamic modeling, 3 or 4 different levels of structural modeling. And the question is, how do you mix and match? If you look at the research literature, a common paper is a very simple structural model and a very complicated aerodynamic model, or vice versa. I'll give you a paper in the journal, but in practice, that's not a sensible thing to do, right? You need, if you're really doing this, you need to choose a structural model and an aerodynamic model that are roughly comparable in terms of their level of physical fidelity. There's no point in using a very elaborate structural model and a very simple aerodynamic model. That's what's usual. There are some exceptions. Okay. Yeah. Oh, I'm sorry. This is lift. Never to be confused with the Lagrangian. This is the Lagrangian. Never to be confused with the lift. What I say is you cannot be a slave to the notation. You must be the master of the notation. You must know what L means in the context in which it's being used. Right? Usually that's fairly clear, but if you've been doing this for a while, you haven't been doing it for a while, maybe less than that. I understand. Yeah, so thank you for asking that question. That's the lift, and this is the Lagrangian. Okay. M sub Y is always going to be the moment about the aerodynamic center plus L sub E. That's true as long as you have a linear aerodynamic model at almost any level of aerodynamic model. But then the lift, in the case of the typical section, is going to be Q times S by definition of some coefficient C sub L. In fact, this equation really defines C sub L. And the reason we want to define C sub L is because we can reason either from dimensional analysis or because we know what the aerodynamic model fundamentally looks like, that whatever the lift is, it's going to be proportional to the Q, proportional to the wing area, and then this thing's a non-dimensional number, which will depend on the Mach number. It will depend on alpha and H in general. It may depend on the entire past history of alpha and H. That is, the lift at a current time may depend on the history of the motion. There's a memory in the fluid, if you will. The aerodynamic force on the wing does not depend on just the instantaneous motion of the wing at the present time. It depends on the entire past time history. Is that related to history? It's not really hysteresis, because this is a linear model, so there's no hysteresis per se. But it is a memory effect. In fact, let me write down a couple of relationships with C sub L. The simplest one is to say it's just dc L d alpha times alpha, where this is the current time, right? And this is some constant. That's the simplest thing. The next simplest thing would be to replace alpha by plus H dot, H dot means time period, right, over U. If you draw yourself a low velocity diagram, you can convince yourself that H dot over U is an effective angle of attack, right? In fact, the fact that this is a plus sign is why that minus sign was chosen for H. Now this was that choice of sign was made by an aerodynamicist. They wanted a plus sign here. Otherwise, if you chose to be positive up, there would have to be a minus sign. Okay, so that's a possible. But then you could also have other terms. You could have alpha dot terms. You can have H double dot terms. By the way, you can't have an H term. Why not? Well, think about it. I'm in the wind tunnel where I'm applied, and I have certain aerodynamic forces on this way. I move it up 10 feet. But if the flow is uniform, the absolute value of H doesn't change aerodynamically. So the lowest time-driven effect at H is always H dot.
Does the whole wing translate with H, or can it be like a...
If it rotates, I take that into account by using alpha. Okay. So H, by definition, is everything is translating uniformly. The whole airplane is going up and down, or the whole wing is going up and down uniformly. Right? If it's doing this, then alpha takes care of that. Okay. Can you see my one flow? And Stockholm probably not. But H means the entire wing or the entire airplane is translating uniformly. Right?
And the typical section model.
Well, in the typical section model, the same thing works for the complete airplane.
Okay.
But now, appropriate to your question, there's another possibility, and that is that the CL at the present time depends on the integral from 0. That's whenever time began. That's whenever the motion began, up to the present time. Now, dCl d alpha, which is no longer a constant, is now dCl d alpha depends on time. And so I write this as T minus tau times alpha of tau. I could also include the H dot, which I won't bother. D tau. What does this say? There's some function of time such that when I multiply it by alpha at time tau, and I sum up all the contributions of alpha from the time when motion began up to the present time, that contributes to the present lift. Okay. This is a convolution. What kind of integral is this? Convolutionary, right? Sometimes it's called Green's function, sometimes it's called a convolution kernel, and it has various names in the mathematical literature and the engineering literature. But physically, we're accounting for the fact that all the motion up to the present time can contribute to the lift at the current time. By the way, the reason we don't integrate beyond T is because if we integrate beyond T, that would imply that the lift at the current time depends on the future motion, which we think is probably not possible, at least not in our world, maybe in science fiction. So there's a so-called causality condition, namely that only the past time motion can contribute to what's happening right now. Historians believe it's right. But engineers do too. Okay. So 2000. Well, that just means I left out a term. If you insist, I'll put H dot here over U. Right? That's the same thing here. Except this is H dot of tau. It's not H dot of T, right? So the motion is a function of what is usually called the dummy time. I don't mean to disparage it. It's an important time. It's the past time, right? And T, so tau is the past time. T is the present. And so one of the things you do when you study aerodynamics is you determine this function. In the context of linear aerodynamics, it's all about determining that function. So once I determine that function, I've got the answer, right? In this case, I'm assuming that this thing has a very special form. What am I assuming about it? Well, it's almost going to be like a delta function, not to be confused with the virtual change of anything. So the point is this was a delta function, and the variable will just give me alpha times t. Right? And by the way, this has a physical interpretation. So we talked about that for a moment. Let's do that. That's interesting. Let's talk about the physical interpretation of this function. Let me write this down again. CL of T equals integral from 0 to T. I'm going to use the notation that's usually used in literature. They usually, when they get to this point, they'll call it K for kernel, right? or sometimes they call it A for aerodynamics. They usually don't call it detail in the PL. But it's the same function, right? Times alpha of tau, d tau. So I want to know what that is physically. I want to understand it physically. I have to be able to compute it from some aerodynamic theory eventually. At least I'd like to. But I want to understand it physically. So, having done this before, let's look at a very special alpha. Okay. Let's look at an alpha of tau. Do not be a slave to the notation, which is equal to delta of tau. That's an impulse. Okay? And let me draw it for you. It's a delta function. I'm going to plot delta of tau. And I'm going to approximate it, if you allow me to, in terms of a discrete representation. It's going to be a function which is something, and then goes to 0. And this little interval of time I'm going to call epsilon. Okay? And the height of this function is 1 over epsilon. Okay? And the area associated with this function, the area under the curve is equal to 1 over epsilon times epsilon. Notice I can cover that in. Otherwise known as 1. So a delta function is something that has a really big magnitude over a very short interval of time. And then the limit as epsilon goes to 0, it has infinite magnitude and vanishing interval of time. But the area is finite. That's the point. The area is finite. So if I put that under an integral, what do I get? Well, this is almost 0 everywhere except that tau is 0. But when I do the integral, it's this thing also evaluated tau equals 0 times 1. So if I put this in then the CL of t due to a delta function is equal to k of t. All right? So that's what k of t is. And if I know k of t, I know k of t minus tau, because everywhere, once I have this function, I can replace t by t minus tau. So physically, this k is the lift due to a very special motion, income. By the way, by integration by parts, if you don't like impulses, you can integrate by parts and convert this into a step function. In fact, if you're doing a CFD calculation, you probably put a step in alpha, right? But a step is just an interval of the delta function, or a delta function is the derivative of the step. The step function is what? It's something that just goes from here up to here, and I want the step function to be a magnitude 1, right? This is a step function in alpha. I want it to be 1. I can normalize it to be anything I like, right? Usually it's useful. Okay. So this can also be useful because people have actually done the experiment. They usually use the step function rather than impulse. Well, there have been attempts to use impulses too. Obviously, it's not an idealized impulse. It wasn't an infinite alpha, right? It was a large alpha with a short interval of time. In fact, it didn't really have to be a large alpha because everything scales, right? If this isn't 1 over epsilon, but this is 10 over epsilon or 1/10 over epsilon, well, the interval is not 1 anymore. It's 1/10 of 10, but that's okay. Everything scales if it's a linear model. Okay, so eventually we're going to have to deal with flutter analysis using that form of solution. So our aerodynamicist, and you will become aerodynamicist if you hang into the end of this course, at least at some level. The aerodynamicist will give us this function, and then we'll use this representation. Flutter analysis, we can help us do a gust response analysis. We can do an endless dispersion analysis. But let's start with the simplest structural model and the simplest aerodynamic model. Get our feet on the ground, or in the air, as the case may be. I guess we want in the air, since we're in a straight tension. Okay. So let me go back to here, just to remind you of what we have. Here are our equations of motion. Here's our moment. Here's our lift. And the simplest possible lift is DL is DCL D alpha times alpha. No H at all. No H dot, no alpha dot, just this. Is this a reasonable thing to do? It turns out it is if the frequency is really small. How small? I'm glad you asked. CL is a reasonable approximation if oscillations, and we're usually looking at oscillations in alpha, are at a small enough frequency. What does that mean? Does that mean 1 hertz? 0.01 hertz? Well, again, you have to think non-dimensionally, because that's the way the theory suggests you should think, and that's the way experiments also suggest you think. It's really the frequency times some characteristic length, which could be the chord, for example, divided by the flow speed. This is known as the reduced frequency. It's really a non-dimensional frequency. Sometimes, in the literature, there's a guy named Struwell. Sometimes it's called the Struwell number. Except using the Struwell number, you take this frequency, which is in radians per unit time, radians per second, and divide by 2 pi, so it's in hertz. Which is unfortunate. Because if you throw away the 2 pi, you lose a lot of the essential physics. It comes from this. It's really when this number is small compared to 1 that this is a good approximation. And if I divide by 2 pi, then if I have omega over 2 pi, C over U, then that's got to be really small compared to 1 over 2 pi. And it's hard to remember that. So, but when you're reading the literature, you need to be sure the author either has the 2 pi in or doesn't. We'll see this later on when we deal with Fourier transforms. There are lots of 2 pi's floating around. Different authors put them in different places. Okay, so this is actually not a bad thing. Now, this thing still depends on Mach number, for example, right? At low speed, of course, it doesn't, but if I get near Mach 1, this thing changes with Mach number, yes.
So this approximation that we have for the lift coefficient is valid for reduced frequency much less than 5.
Right.
And we're using this for a flutter analysis.
Right.
However, it's not present of a flutter that typically occurs at higher reduced frequency.
It could. Yeah, the reduced frequency will turn out to be whatever it is. So when you use this model for the aerodynamics, among other things, you'll be able to compute the reduced frequency after you've done the flutter analysis. And you can find out whether it's small enough or not. If it is, you say, great, I had a good day, I'm going to go home. If it's not, if the reduced frequency that you compute from the flutter analysis using this model is high enough, you say, I got more work to do. That's often the case in mathematical models in general, certainly in aeroelasticity. You make certain assumptions, and then after you get the answer, you should check whether the assumptions are met or not. And again, if you're experienced, you probably are better at making the right assumptions. Or even if you're experienced, you may make simplified assumptions, hoping that this will come out okay. Because I can get this answer in 2 days. And if it comes out okay, I'm done. Whereas the other answer may take 2 months. And if it takes 2 months, it takes 2 months. But I probably don't want to start off with a 2-month calculation. If I have any reasonable hope that a 2-day calculation. Okay. Okay. By the way, one last thing. I'm getting a preview here of the answer. One last thing. And I have a little more room on my paper. If I have a typical section model, if I have a high aspect ratio, by the way, this also depends on the aspect ratio and the shape of the wing platform. But for the typical section, I'm thinking that this is being, or even our simple wing model, I'm thinking of span being very long, chord being relatively short, so I have a high aspect ratio. So in that case, CL basically just depends on Mach number. So I'll tell you the two classical formulas for DCL d alpha as a function of Mach number. And it turns out it depends on whether Mach number is greater than 1 or less than 1. Okay. Okay. So if the Mach number is less than 1, DCL d alpha is basically 2 pi. See? What's the 2 pi is going on? 2 pi divided by the square root of 1 minus m squared. Okay? If the Mach number is greater than 1, it turns out to be, and we'll see this when we do our aerodynamic portion, of course. It turns out to be 4, not 2 pi, but in the range of 2 pi, right? It's the number, and that's the number, divided by the square root of m squared minus 1. Right? Well, we wouldn't want the m to be greater than 1 here because that gives us the imaginary number. We'll take the square root vice versa, right? On the other hand, both of these formulas tell us that something really bad is happening when the Mach number goes to 1. Both of these formulas blow up. They really tell us that DCL d alpha, that the number is going to 0, becomes really large, which it does. But it doesn't go to infinity. It doesn't go to infinity. But linear theory, classical linear theory, which assumes that omega c over u is really small compared to 1, tells us that things blow up. The good news is now, if omega c over u is not 0, then there's some extra terms that prevent this from blowing up. On the other hand, if omega c over u is small compared to 1, the linear theory doesn't blow up, but it gives you an answer that's not very good. So right away, just looking at these simple formulas, that tells us that something challenging is happening in Mach 1. And this is Murphy's Law. Usually, flutter is critical in the range of Mach 1, and that's what the classical linear theory tends to break down. That's why people are still doing research on transonic theory. Okay, including our group here. Okay, now are we ready to do a flutter? Now we got time. At least for our typical section. So we're going to, I'm just going to carry this along with something called coefficient. It may depend on Mach number. It may depend on. Okay. So let's see what we have. And as usual, I'm going to set this to 0. Remember, this doesn't depend on the motion. It doesn't depend on h or alpha, right? So it turns out it doesn't influence within the framework of this mathematical model. Whether this is there or not, it doesn't change whether the system is dynamically stable or not. So now we have m h double dot plus k sub h, h again, plus s alpha, alpha double dot, minus L, so I'm going to bring it on this side, so it's going to be Q, S, DCL, D alpha times alpha equals 0, and that's it. I alpha, alpha dot, plus K alpha, alpha, plus S alpha, H double dot, it's equal to plus M sub Y, so it's minus M sub Y, which is minus Q, this is minus the left times E, right? So it's minus Q, S, E, DCL, D alpha, alpha equals 0. Okay? So this is just about the simplest form of the equations we can use for coupled mode flutter. we call that, well, no. So this is sort of the simplest prototype. Well, let's look at a special case. It's always good to look at special cases. We simplify things a tremendous amount already, but let's look at an even simpler case. Special case is S alpha is identical to 0. Remember, that means that the center of gravity and the elastic axis are on top of each other. You may not be surprised to know that sometimes people design things when they have the flexibility to do something to make this happen. Why is that? Because if this term goes away, then these two equations are uncoupled. If I use this simple aerodynamic one, right? I can solve this equation for alpha, and then after that, solve this equation for H. It turns out that under that circumstances, the H motion is never unstable. But this motion can be unstable, but it can only exhibit divergence. Remember, divergence is when this term and this term cancel with some magic letter Q. So this dynamic equation for this situation says the only thing that's bad that can happen, the only instability that can occur is divergence. Okay? So if I want flutter, at least this kind of flutter to go away, I just set that to 0. And so sometimes a typical flutter solution from the designer's perspective is, if I think I have a flutter situation, I add some mass and I move the center of mass to where it aligns with the elastic axis, right? And then I might still have divergence. At least I don't know. At least not this kind of thing. What about single degree of freedom flutter? Well, I mentioned that the other day. I'll just remind you of this. If I have single degree of freedom flutter, the only way I can get that is if in this term, even with S alpha 0, if I, in addition to this representation of the aerodynamics, I also have an alpha dot term with the appropriate sign of the coefficient, right? Mm-hmm. So if I replace this by QSE DCL D alpha times alpha, and then I assume I have another term like this, and if this sign is what? What would the sign of this term have to be if I put this in here to give me negative damping? Well, I already got minus sign, so this is positive, that's negative damping. If it's negative, then it's positive. And by the way, remember I had this wonderful general model. That entire past history implicitly has in it damping, aerodynamic damping. But when I use this model, it's not so obvious, at least at the present time, whether the damping is positive or negative. But if I use this, I could, and even for S alpha 0, I could, in principle, time march this equation, right? I could go over to my friendly MATLAB software and run the kind of solution, including this time history, if I know the K function. Find out whether the solution is growing or decaying. All right, so what this tells us is coupled mode flutter never happens when this is true. And therefore, if you don't want coupled mode flutter, this is a famous condition for making, at least for this simple model, making sure that coupled mode flutter doesn't happen. Now, sometimes the chief internal will say, I'm not going to add that. It's terrible things from there, but you've got to come up with a better solution. So then there's a discussion. But this is something that people often look at. If the mass required to do this isn't too large, that's a good way to go. Okay, now, for general case, if you will. We're still going to use this simple aerodynamic formula, but now S alpha is not. So, flutter analysis. In almost any kind of linear flutter analysis, the first thing we're going to do is we're going to take alpha, a function of time, and assume it's some magnitude, which we don't know yet, times e to the beta t, where beta is something we don't know either. As I mentioned the other day, we hope to know it. In general, it will be a complex number, and the real part will tell us whether things are going to grow or decay with time. The imaginary part will tell us if there's what the frequency of oscillation is. And then, once we know the frequency, we can compute the reduced frequency and see if our original assumption about the aerodynamic model was okay or not, right? So it's important to know the frequency too. And then you can do the same thing for H, of course. H bar, e to the beta t. These betas are the same, of course. They have a common variation in time, and you can show for any system that's the general case. So we put that into these equations, and we try to determine beta. And once we determine beta, we can say whether the system will work or not. Notice that the beta will depend on Q. And so what we think will happen is, for small q, the system will be stable. And if the Q is large enough, it will become unstable. Huh? Okay, so let's do that. So let's call this equation, these two equations together, 1, and these two equations 2. So now if I put 2 into 1, I'm going to get some common factors, alpha bar, H bar. I'll get some common factors, either beta t. I can cancel out all these beta t's. I'll do that. And therefore, I can write these as linear algebraic. These differential equations, once I assume the solution of this form, will become linear algebraic equations for H bar and alpha bar, right? Where the coefficients equations will involve Q and beta and lots of other things. But the principal thing I want to know is how beta varies with Q, right? For given values of mass. So what does that look like? Well, the first equation is beta squared m h bar plus kh h bar plus beta squared s alpha bar plus q s dcl d alpha bar equals 0. Again, I've canceled out all the e's and beta 2 terms. The second equation will be beta squared beta squared I alpha bar plus k alpha bar plus beta squared s alpha h bar and so forth. Okay. But I can also write that in matrix notation, with what every good flutter engineer must do. And so, in matrix notation, it's a 2x2 matrix, right? Because it's a matrix equation. So I have H bar up here, I have alpha bar here. On the right-hand side now I have zeros. And I have, over here I have what? Beta squared m plus k sub h, beta squared s alpha, plus q s dcl d alpha. Over here I have beta squared s alpha. I have beta squared I alpha plus k alpha. Minus QSE DCL D alpha. Okay. So this is, I'll call this equation 3. One possible solution, the mathematics is the same, but the physical interpretation is rather different. One possible solution is H bar and alpha are both 0. That's not the interesting solution. The other interesting solution is when they're not 0. When they're not 0 is when the determinant of this matrix is 0. And when the determinant of this matrix is 0, that gives me an equation to determine the betas. And it will be a quartic in beta because I've got beta squared times a beta squared here, right? But the good news is, because of my simplifying assumption about the aerodynamics, it's only a quadratic in beta squared. So I can use the quadratic formula to find beta squared, and then if I can take a square root, I can find the beta. So there are 4 bases. 2 beta squareds, there's 4 bases. And if you plot the results, I've done this before. If you plot the results, they look like this. And I'm going to plot them versus Q. Oh, thank you. And here's beta. And there'll be complex conjugates, by the way. So there'll be one solution here for beta and one solution here. And since I've omitted, thank you. Since I've omitted all damping in this system, the betas will be purely imaginary numbers to begin with. Okay? And they will appear in conjugate pairs. So this one has its negative counterpart, this one has its negative counterpart. Usually people only plot the upper half because it's just a mirror image, right? And then as Q gets large enough, this one goes down, this one comes up, and they meet. And then after that, they stay the same. I hope I can draw this in that. Right? And what happens here is, now there's a real part. And one of the real parts will be positive, and one will be negative, and the one that's positive means I'm unstable. Right? So this is the floater point in this simple model. And that's why coupled mode clutter is sometimes called merging frequency clutter or coalescing frequency clutter. Oh, that's right. Yes.
Why is that clutter point if in beta I for each mode is already positive?
No. Well, let me draw you the rest of the picture. Now I'm going to plot the real part. Remember, beta is a real part plus I times an imaginary part, right? So I plot the imaginary part here. The real part, with this simple model, up to this point, the real parts are all 0. There are 4 of them, but they're all 0. And then they split. One goes positive, and one goes negative. Actually, 2 go positive and 2 go negative. Right? It only takes one positive real part to make the system unstable. Okay. Now, what would happen if I put a little bit of damping in? That would correspond to putting in an H dot term or an alpha dot term or something like that. Well, things change a little bit. First of all, these frequencies never quite come together. They tend to come together, but they never quite merge, right? They come together and then they go off close to each other. Down here, beta R is not 0 up to this point. If you're lucky, remember there are 4 beta R's. If you're lucky, they're all negative. They're small enough here. But then, I'll draw you a ball called the critical clutter branch. Let's say they go like this. Dotted line means adding damping. I'm adding some damping. It could be structural damping, by the way, as well as aerodynamic damping. Although mostly, not only, but mostly aerodynamic damping is dominant in structural damping for aeroelastic analysis. So it would be positive, it would be negative, indicating a stable system. And then there might be 2 of them that come pretty close together, and then they go off like this. And maybe the flutter point would move a little bit from here to here, right? If this were always the case, you'd be tempted to always throw away aerodynamic damping or structural damping, right? Unfortunately, there are cases where adding the structural damping to this model, quite aside from more elaborate models, actually destabilizes the system. The flutter Q goes down even though I've added positive damping to the system. And it has to do with the fact that I'm dealing with 2 coupled modes. So I may have added positive damping to one mode, but since they're interacting, that energy associated with positive damping in one mode can lead to an unstable system in the coupling. mode system. And that can happen, by the way, with structural damping models, as well as aerodynamic damping models. It's controversial even to this day whether that's, in the case of structural damping in particular, whether that's a physically viable result. Then some people say when you have structural damping and it destabilizes the system, it's because of all the structural damping. It's not a good model. Okay. But it was a good model when you didn't have aeroelasticity. It was a good model when you just had pure structural dynamics. So why is it all of a sudden I don't like that model? Right? Something people talk about. Okay. Now, the good news. These pictures I've just drawn will still work when I do the wing model, right? When I now go to a more elaborate model of the structure. They still work if I went to a plate model. They still work usually when I go to a more elaborate aerodynamic model at various levels. Right? So qualitatively, this is the kind of thing you look for in any flutter analysis. I'm looking for frequencies that are tending to come together. If I think the coupled mode flutter is an issue. If it's single degree free flutter, what happens in the turbulent regime? These frequencies don't come together. These frequencies tend to just pretty much stay the same as Q moves out. But the damping changes. It goes from being slightly in the stable regime to slightly in the unstable regime. And single degree of free flutter is notoriously more difficult to predict accurately because we're talking about small levels of damping, small stable levels of damping that convert to some value of dynamic pressure to small unstable levels of damping. And that's just harder from the aerodynamic theory to handle. Whereas this kind of flutter is sometimes called strong flutter because once this thing goes unstable, I mean the magnitude is really large, right? And usually at this point it doesn't change very much when I add a little bit of damping, either aerodynamic or structural or coupled mode. It may change some, but it doesn't change a tremendous amount. So, in general, coupled mode flutter is better predicted by the math model. And single mode flutter is usually a more challenging proposition. Okay.
Yes. You said this can be used like with a plate model.
Yeah.
Like, is there still like an A bar and an alpha bar? It's just different.
Thank you for answering that. It's just like we rehearsed it. I mean, came across very fun things. Here's what we're going to do. In this model, first of all, we'll do this model, and then we'll do the plate model. In this model, what do we have? We now have H still, but it depends on Y as well as T, right? Where this is Y. The alpha still depends on Y and T. Okay. So what we're going to do in that case is we're going to take H up, alpha Y, not alpha. If it were a function of alpha, that would be simple. Okay. We're going to take this and use the Bailey-Ritz method. We love the Bailey-Ritz method. So we're going to have this as, I'll call it H sub n of T. This is a function of T. No, better use this notation. H sub n of T times H sub n of Y. Where these are some functions, H sub n of Y, which I will cleverly plot. For example, they might be the natural modes of the structure. And the same thing for alpha, right? In the case of the delta wing, I can't use H and alpha anymore because it's not just bending of elastic axis and rotation of the axis. Now I've got to use some general deflection W, which depends on X as well as Y and T. So this is the X direction, this is the Y direction. But I can still, I'll call it Q sub n T, not to be confused with dynamic pressure ever, right? Times some other shapes which depend on X and Y. Where again, these are probably the natural modes of this plane. Since I could compute from, I can use regular bits to compute those, but I could also use the fine element. So now I'll end up with differential equations in time for these coefficients, a sub n in the case of this case and c sub n cases. But I'll still have the same form of the equations. And if I use a simple aerodynamic model, I'll still get bending, torsion, flutter, or 2 degrees of flutter and all that. So I can do the same kind of thing.
So with your second degree of freedom, just be like a second variable with like the deflection.
Well, if I want just a 2 degree of freedom flutter model, in this case I would just use one term for h. And I'd use one term for alpha. Oh, b sub 1, alpha 1 of 1, right? Where this would be the first bending mode of my beam rod, and this would be the first torsion mode of my beam rod. And I would end up with a form of equations that's identical to what we just discussed. But if I have to use 17 mode, or whatever the number is, I'm going to have a lot more equations. But qualitatively, I'll still be looking for 2 frequencies coming together. Now, it could be that it might be the 5th and 6th frequencies to come together. It doesn't have to be the first 2. Often it is the first 2, but there are well-known cases where it's not the first 2. Okay. So, if you're going to do this model, it'd probably be good to use at least 3 or 4 torsion modes, just to be sure. And that's even more the case when you have a plate model, where it'll be even less obvious which modes might prove to be most in fact, currently there's a lot of interest in very high aspect ratio lens for timing purposes. So if this L gets much larger, if L over C gets very large, it turns out that it's always usually the first torsion mode. But as L over C becomes higher and higher, it's a higher and higher bending mode. So it's first torsion and third bending. That's critical. And then if I go to a higher aspect ratio, then it's fifth bending and first torsion. And that's been observed both in experiments. Okay. I think I'm going to stop here for the day. We've done quite a bit. But before I stop, let me see if there are further questions. Stockholm, you've been remarkably patient and quiet, and we appreciate your hanging in there. Do you have any questions before we conclude for the day?
No, there are no questions.
None. Okay. Well, what about Europe? Okay. Then we'll stop here, and we'll go on with some of the more elaborate models the next time, a little more detail.